Okay, so this is the final part of the chapter, first law of thermodynamics, and it is specific heat for solid and liquid, right? So let's begin. So the thing that is different for solids and liquids is that delta V is zero. That is, they are incompressible, right? You can't compress solids and liquids, at least not to an appreciable extent. So for ideal gases, we saw that Cp was greater than Cv, right? But here Cp is same as Cv, and we, instead of writing Cp and Cv, we just write C, specific heat. So Cv is del U by del T at constant V, which means U is a function of temperature here as well. Cp is del H by del T at constant P, but H is a function of pressure and temperature here, whereas it was just a function of temperature before. So what you need to remember is that du equals to c dt is still valid here, and delta u is equals to c average delta t. C average is the average specific heat that you remember in the last lecture there was one question where it told us to calculate the uh, delta u using the average temperature. This is that C average, the specific heat calculated at the average temperature, right? Or you can just integrate this if you have a constant temperature and all that. Du is mostly the same. However, dH equals to du plus v dp. Also, this is small u because obviously there is no mass. If you wanted capital U, you would multiply it by m, so you would get mc dt and mc delta t, right? Always be mindful of the units. As I've said before, I like to solve questions without mass in them and then multiply mass in the end. But you have to find your own way of solving, right? Mm, So dH is written as du plus v dp, or delta H equals to delta U plus v dp. For liquids and solids, the specific volume is very less. So the delta U term is a lot greater than the v dp term. So dH is equals to du is equals to delta H is equals to delta U, because this can be neglected. However, there are two special exceptions to this case, when that is when we cannot neglect the VDP term. Pump, because the process in pump is isothermal. But a large pressure change is applied in a short time, because obviously you want to move a large amount of water very very quickly through a pressure difference or a gradient difference, right? A large pressure change is applied, which means dp term cannot be ignored. In the pump, delta U is 0. So, because remember isothermal process, so dt becomes 0, hence delta U becomes 0. So in pump, delta H for pump is V delta P. Right. And that was pretty much it for specific heats of solids and liquids. Now we're going to solve one or two problems that I have. Starting with a simple one. 1.5 kg of liquid having constant specific heat of 2.5 kilojoule per Kelvin, kilojoule per kilogram Kelvin, C equals to 2.5 kilojoule per kilogram Kelvin, is stirred in the conducting chamber, causing the temperature to rise by 15 degrees, delta T equals to 15. During the process, 1.7 kilojoule of heat is transferred from the liquid to the surrounding. Okay, so the system is the liquid. Let us take the system to be the liquid. So the sign of heat will be negative because the liquid is losing heat, right? So delta Q equals to negative 1.7 kilojoule. The reason I write kilojoule everywhere is because when you don't write, you don't know if it is in joule or kilojoule, and when rechecking the question, you will get confused. So first we have to depict the energy interactions happening at system boundary. Not doing this. Find the change in total energy of water. Assume specific heat to be constant at room temperature. So delta U equals to mc delta T, or du equals to mc dt. As the specific heat is constant, we can write the delta terms instead of the d terms, right? This gets converted to this basically at specific heat. Specific at constant specific heat. Right. So delta U equals to 1.5 into 2.5 into 15. Yeah, using the unit of temperature change doesn't matter. So it will come out to be 56.25 kilojoule. I would normally recommend doing calculations in joule, but when you don't have any interconversion necessary, since your specific heat is also given in kilojoule and your everything else is also given like that, might as well solve everything in kilojoule, right? Why convert to joule and convert back? However, this only works for very, very simple applications, so I won't recommend it, right? Find work done. So we'll use the first law of thermodynamics, delta K equals to delta U plus W. And upon solving this, you will get work done to be minus 57.95 kilojoule. Okay, fairly simple question, right? So now let's move on to a more complicated one. Well, not complicated exactly, it's still kind of simple only. Consider a copper block with density equals to 8300 kilogram per meter cube and C equals to 0.40 kilojoule per kilogram Kelvin. Okay. Of cross-sectional area 2000 centimeter square, A equals to 2000 centimeter square, which is equals to 2000 into 10 to the power minus 6 meter square, which is 2 into 10 to the power minus 3 meter square. I'm converting centimeter into meter because that's the standard SI unit. And thickness 3 centimeters. So T equals to 3 into 10 to the power minus 3 meter. It has an electrical heating element of capacity 5000 watt. Okay, so let me just draw the block real quick, right? This is inside the copper cube and it has a capacity of 5000 watt. The heating element is switched on and the block starts getting heated up. During the process, the block is losing heat to surrounding at rate of 1000 watts. Calculate the temperature of the block after 3 minutes if initial temperature is 30 degrees Celsius. Okay, so there's a few things going on here, right? So the heating element is heating the block at a rate of 5000 kilowatt. So Q in, the rate of Q in is 5000 watt plus because it's going in, and the rate of Q out is minus 1000 watt. So the net rate of Q is 4000 watt. The net rate of heat exchange is 4000 watt, right? Also, delta T is 180 seconds and T1 is 30 degrees Celsius. So what do we do? So what we do is that we notice that the heat flowing in is not in fact the heat flowing in, it is the work done by the heater. So we can see that the heater is doing work, and we have been given some value of the heat that is being lost to the surrounding. So work is there, heat is there. It is only natural that we try to apply the first law, right? Delta Q equals to delta U plus W, right? So delta Q is plus delta Q is minus 1000 because that is how much it is losing heat, and into 180 because the total time elapsed is 180 seconds, and we are trying to find energy, and we're not writing it in terms of rate, but in fact we're writing it in terms of total energy, right? So if we multiply the rate of doing work into the time, or the rate of losing heat into the time, we will get the total energy. Delta U plus 5000 into 180. But the sign of work here will be minus. Earlier I had said that it was heat, but it's not heat. The heater is doing work, and it is with respect to the system, work is being done on it by the heater, so the sign will be negative, right? So you will get some value of delta U. And if you remember, for the solid copper block, delta U equals to mc delta T. Again, as specific heat here is constant. So mass can be found by density into volume, or density into area into thickness. All of the values which we have been given. And if we plug these in, our T2 will come out to be 339.1 Kelvin. And with that, we conclude our chapter of specific heat and solid, of solids and stuff. And the first law of thermodynamics chapter ends here. After this, you have transient process, which doesn't really have a whole lot of theory at all. It has most of the questions. So for that, I recommend you attend the tubes. And for now, I'm out of time to make more videos. I, in fact, have to go back tomorrow. So yeah, I hope this playlist helped you, and if it did, always like, subscribe, and share. Please don't gatekeep this playlist. I highly encourage you to share it with your batchmates and all, because that is how you get to know people, right? By helping them. So yeah, I hope this playlist gave you a leg up in thermodynamics and helped you understand the basics. And yeah, see you later.